grids with high penetration of renewables. A lot of what I will be talking about today is based on the recently released book on the topic of renewable energy integration. And so most of what we will cover will be excerpts from the book, but we'll also try to interweave in the discussion some of the ongoing and pressing issues that relates to the subject of renewable energy integration. In terms of an agenda, I'll give a quick background to the book, how it all started, share with you the list of contributors, and an overview of the book covering some of the key features, the 10 key parts of the book, highlighting the sessions in the book where you have some case studies, and then talk briefly about basic power system operations, just a few slides, just because we have a very broad audience of people with a very diverse background. Not everyone on the call might be familiar with all the intricacies of power grid operations, so we'll take some time to run over that quickly. And then we'll get into what I would like to focus on this morning, which is the issue of power system flexibility, talk about it, what it is, some of the needs, the sources of flexibility, highlight some of the methods for analyzing flexibility, give a few examples, and then end with a future outlook where I will focus on 3 key areas that I think are very relevant for the future growth of renewables and the integration of renewables onto the power grid. So in terms of the background, the idea of this book goes back to the result of a study that was done for the United States Department of Energy. And the goal of that study, which was done about 4 years ago, was to basically explore what was going on in terms of integrating renewables from the standpoint of grid operators. The objective of the study was to explore and basically capture the best practices in terms of what was going on from the grid operator's perspective. The reason why we did that study, because for at least a decade, we have been hearing a lot of concerns about the impact of renewables on the grid, and there were all kinds of opinions about it. And so we decided, with the support of the U.S. Department of Energy, to go out and survey the world and find out exactly what the grid operators were thinking, what were some of the concerns, and what were some of the solutions they've used to integrate renewables from an operational perspective. The study basically resulted in what we consider to be perhaps one of the most interesting gathering of data. We had 33 grid operators participate in the study coming from about 18 countries, and totaling at the time about 72% of the installed capacity around the world. And this was very important, having this diverse group of grid operators, because again, the objective here was to really highlight for everyone the importance of renewable energy integration from the perspective of the grid. Key elements that resulted from that study were, 1, the need for forecasting, 2, the need for decision support tools to integrate renewables, 3, policy and regulation, 4, flexibility, and the last element that came up from that survey had to do with the role of the workforce. And following the study, we got a lot of interest expressed in terms of why don't we do a follow-up study, and there are discussions about a potential follow-up study. But in the interim, there has been a very clear increase in the level of activities on the side of integrating renewables from a whole range of issues. And so as a subsequent follow-up to this study, a request was made by the publisher, Elsevier, if we could put together a book on this topic. Now, given the very diverse nature of renewable integration, writing such a book on a study like this, on a subject like this, would require the participation from a broad audience. And so what we did as part of preparing the book was to basically reach out to the best in class and some of the world-leading experts when it comes to renewable integration. We did that, and we were able to get almost 60 contributors who submitted single chapters or co-author various chapters on the book. You can now see the range of participants and contributors to the book, and they came from all over the world, from the U.S., from Europe, from India, from Africa, from Latin America. We pretty much had all of the, I would call it the top brass with regards to renewable integration in the world decided to contribute to this book. And as a result of their contribution, the book, once was released, has received a significant amount of advanced praise for the book. And this is important because oftentimes when you write a technical book, the reception of the book is merely targeting a technical audience. This book, on the other hand, targets not just a technical audience, but also an audience that involves regulators, policymakers, investors, and what have you. And so as you can see, the book received a lot of advanced praise and compliments from folks both from the technical side, folks involved in policy, folks from the financial industry, and others. So all in all, this shows you with the breadth of the contributors to this book, as well as the depth of the advanced praise in terms of the expertise we've received, this book is clearly one that is timely and is getting a lot of feedback and a lot of interest from around the world. Now, let's just get into the book itself and give you a quick overview. The book basically addresses three sets of issues. First of all, it addresses all of the key issues around integrating renewable into power grids and markets. And this is important because a lot of the discussions around the integration of renewables is typically linked, or not linked, but is typically only focused on the physical aspect of the grid and not the market aspect. And I think what we've done in this book is to highlight the importance of both the markets as well as the grid. The other thing the book does is that it does capture the various challenges regarding operational integration as well as planning and some of the regulatory issues. Because we wanted this book to be theoretical but also very practical in its nature, the book involves several case studies that have been written by grid operators around the world, tackling various issues using different methods to provide solutions for dealing with the challenges they're facing. And then lastly, because of the need to integrate renewables and take advantage of the advances in technology, the book also looks at emerging technologies, disruptive technologies that will be useful in the management and operation of the grid once you have high levels of renewables. So in essence, you can summarize the 5 areas that the book touches upon: the physics of the grid, the operation of the grid, the markets within which grids operate, and the need and the use of information technology. And then lastly, and perhaps most importantly, is the role of policy. So throughout the book, you will see that almost every chapter has some implications or explores some of the implications of policy, but nonetheless, all of these are interrelated. So the physics, the operation, the information, and the markets aspect of the grid ties into the need for policy and how policy should be put in place. The book is divided into 10 parts and totaling of about 35 chapters. So it's a pretty comprehensive book in that regards. The chapters, beginning with the chapter on policy and regulation, where we have 3 chapters, one written about Europe, it's written by Helena Lindqvist, and we also have a chapter in the book on policy with regards to the United States. We have a chapter in the book with regards to policy in Africa as we see increasing interest in renewable energy in Africa. And then there's a chapter on modeling of variable energy resources, and this chapter explores the modeling issues. And then part 3 in the book deals with this issue of the impact of variable generation on power systems and markets. And this is looking at some of the operational impacts as well as some of the impacts in terms of the interplay between policy and operation. Forecasting renewables is the next part of the book, which has 3 chapters. As you all know, forecasting variable generation is key to being able to successfully integrate renewables, and so we've dedicated an entire section in the book to this topic. Besides the forecasting, the next part of the book deals with this issue of connecting renewables to the grid. And here we have 3 chapters again, one that looks at integration from the standpoint of using high voltage direct current. And then we also have a chapter that is written with a case study from India that looks at some of the renewable energy integration issues. Part 6 of the book attacks the issue of flexibility, which is what we'll spend some time on today. And system flexibility becoming a very key issue. Is a key issue at the IEA. It's a key issue in many countries around the world. It's a key issue being addressed as part of what is being termed as the 21st Century Power Partnership. All of these different entities and organizations around the world are singularly focused on understanding and addressing the issue of flexibility. And that is the subject we will spend most of the time on this morning. Demand response and distributed energy resources is also addressed at length in the book. We will talk about demand response and DER later on in the presentation today, because these two mechanisms can be used to provide flexibility to the grid as well. Because we know that variable generation is being deployed not just on integrated networks, but also on island systems, there is a section in the book with 3 chapters dedicated to the issue of island power systems. Island power systems are unique in the sense that the issues they encounter are not similar in most respects to that of a bulk system. And so we decided to make sure that these issues are addressed in this part of the book. As renewables expand beyond wind, solar, hydro, and we're seeing more tidal wave and wave energy, there is a part of the book that looks at these emerging types of renewables and looks into some of the issues and solutions for integrating tidal and wave energy, as well as other forms of emerging renewable energy technology. And then the last part of the book looks at some of the enabling and disruptive technologies for integrating renewables, looking at things like big data and how can big data be used to accelerate the use of renewables, as well as looking at things as monitoring and sensor systems, so-called synchrophaser, which allows you to get better situational awareness, and also allow you to integrate wind forecasting into the operation of the grid. So these are the 10 parts of the book. And interspersed between those parts are the 35 chapters. And I must say some of these chapters are fairly theoretical, but then some of them are based on case studies. And the case studies in the book comes from Brazil. There's a case study that looks at the issue of mini grids and mini hydro and how they function in the context of a microgrid. There are 2 case studies, if you may, from Denmark, looking at some of the operational experiences in Denmark with regards to integrating renewables. Germany, there's a chapter in the book from Germany that looks specifically at the role of PV and how some of the challenges that were initially faced in the German PV sector with regards to the impact of PV on the grid in terms of not having the appropriate level of controls in the inverters. These issues are addressed in the case study from Germany. There are 2 case studies from India, one that specifically looks at the role of the bulk power system, and there's another case study that specifically looks at the integration of a wind farm or multiple wind farms in a more regional system as opposed to the bulk power system. The Indian case studies also looks at the issue of policy and explores the various policy measures that have been used in India and that are being used in India, and look at some of the successes and challenges that still lies ahead. South Africa, because of the increased penetration of renewables in South Africa, there's a case study in the book from South Africa written by Richard Candy. And that case study focused primarily on the issue of increasing situational awareness in terms of integrating forecasting information into the grid, in terms of visualization of high penetration of data into the control center and what that does in terms of integrating renewables. And then from the United States, we have 4 case studies. Those 4 case studies actually reflect the geographical difference. There is a case study from the East Coast, from PJM, which is in the eastern part of the United States, where we have the largest electricity market being PJM. There is a case study from Texas that was written by colleagues from the Electric Reliability Council of Texas, ERCOT, that looks at some of the issues in ERCOT. There is a case study written from California that looks at some of the issues as California looks to increase in their penetration level of renewables to about 33%. What are some of the issues with regards to reserves and those things? That particular case study really digs into the famous now, perhaps for many of you, so-called duck curve that looks at what happens when you have high penetration of variable generation onto your system and the impact that has on reserves. And then lastly, there is a case study from the Pacific Northwest. Those of you who are not familiar with the Pacific Northwestern part of the U.S., that is a system that is highly hydro-based. And so that case study looks at the use of demand response and other forms of distributed energy resources to help address the issue of variable generation onto the grid. So that's a pretty good synopsis of the book in terms of the content. What I'd like to do now very quickly is to just share a few slides to highlight the essence of basic power operations and then dive into the issue of flexibility, which is the focus of today. The power grid has not changed in essence from the time it was first envisioned 100 years ago. So this chart basically shows you that pretty much everything has still the same in terms of the physics of the grid. What has changed and what is changing is the operation of the grid as well as the integration of new technology that is bringing what is referred to as the smart grid, which is basically the use of information technology, controls, and sensors to make the grid smarter, and that allows greater use of information technology to better operate the grid. And so the evolution of the physics of the grid may not have changed as much, but the integration of information technology, control systems, along with other types of new technology, is creating this new grid where you will have all kinds of interesting phenomena occurring. And so we see this evolution where information technology is meeting the physical grid, and that is bringing about the change. But in essence, with or without the smart grid, and with all the new technology, power system operations basically hinges on two things. How do you balance supply and demand? And so as you envision the issue of balancing supply and demand, which is the core of operating the grid, what is important is that for an operational perspective, how do you reduce the impact of variability and uncertainty to reduce the imbalance that is in the grid? So in real time, constantly, operators have to make sure that the grid is kept in balance, and dealing with this imbalance is the key issue for operating the grid. Now, how does this then affect, or is this impacted about with regards to renewables? Well, what is happening is the grid of the past, and by the past I mean before you had higher penetration of variable generation, the main thing on the grid that was moving was the load. And so the variability of the load was something that people understood and have been able to deal with over time. What is changing now, and what is making the balancing a much more challenging topic, is now because you have not just the load that's varying, but you also have the generation. And so you have this very interesting situation where you now have the simultaneous variation of generation and load. And both of these variations are now subject to uncertainty. And so from an operational perspective, how do you operate a grid where you have generation that's variable, load that's variable, and you have uncertainty in the prediction or the projection of the amount of generation you will have online, and also to some extent even the impact of the load? And so this issue of balancing the system is the challenge. But if you look at the grid at large, there are a couple of other issues that are very important. We've already talked about balancing. We've brought up the issue of variability in terms of both generation and load. The issue of uncertainty as it relates to variable generation, whether it's wind or solar, the ability to predict these resources, making sure the grid is stable, making sure you have adequacy in terms of having the amount of power that is needed over a given period of time to secure the stable operation of the grid. And then lastly, the issue of flexibility. How do you make sure the grid is flexible? And why is this flexibility such a big issue today? And why it is an area of key focus? So I'll spend the rest of this presentation looking at this issue of flexibility, which I think at this point in time is perhaps one of the hottest areas of research, hottest areas of focus, both from a regulatory standpoint, from a market design standpoint, but also from a policy standpoint. So let's talk about power system flexibility. What is it? So flexibility from a power system perspective basically seeks to express the extent to which a power system can increase or decrease the electricity production or consumption in response to variability, whether the variability is expected or unexpected, and that is to say under uncertainty. So in essence, what we're trying to do, if you remember, trying to maintain this balance of supply and demand. In maintaining the balance of supply and demand, we expect to have some uncertainty. We expect to have the situation where generation and consumption may vary in ways that we may not anticipate. How do we then have a grid where you can move megawatts up and down in response to this variability that is caused by whatever event in the system that's causing this variability? So that is in essence what we're trying to do here. Manage the variability, manage the uncertainty, but do it in a way that flexibility is maintained so that the grid continues to be stable. So what is all flexibility? What are the needs and what are the sources? What caused the need of flexibility? We've already talked about demand variability. We're not talking about variable resources as one of the needs for flexibility. That is if you look to the left side of the chart that's on your screen. Now, that's the needs. Those are the things that are driving the needs. And then to the far right, you have the sources that can help provide flexibility. Traditionally, we've been able to get some flexibility from power generation plants, everything from hydro plants, from gas turbines. Fast devices on the system have been sources of flexibility. Because again, remember, the flexible resources, the resources that are providing flexibility must be able to move up and down in response to variation on the load, the generation, or any other contingency we may have on the system. Demand response is also one way to bring about flexibility. No surprise, because we're moving loads up and down in response to variability. Energy storage is becoming a much more interesting component of this set of resources that can provide flexibility to the grid. And then obviously the physical grid itself, the interconnection of the grid with other systems or the integration of different markets also can provide a level of flexibility. What is important with this framework, which was initially developed by the IEA, is that we have to look at flexibility in a more holistic view, and that is to say, look at flexibility through the lens of the market, through the lens of system operations, and through the lens of the grid hardware. Those are the components that we need to look at as we explore flexibility. Now, from the standpoint of analyzing flexibility, you can imagine that the power system, any power system, has huge amounts of devices, a lot of devices that can move up and down, a lot of devices that can contribute to flexibility. So one of the key challenges, like I said, facing the industry right now is how do we analyze the available number of, or the available amount of operational flexibility in a power grid? There's a lot of work being done around the world. Different labs are looking at different methodologies. In the book, one of the chapters that looks at flexibility is a chapter that was contributed by Professor Goran Anderson and Andreas Ulbeck at the ETH in Zurich. And this methodology, which I believe is one that has a lot of potential, as you can see, it looks at all of the different types of flexibility resources, the conventional power units, energy storage, demand response, wind and solar, okay? And then it also looks at the resources that can be dispatched. So everything from pump storage, batteries, electric vehicles. Basically, it looks at any component on the system that has the ability to move up and down. It takes these systems, these different devices into consideration, and then attempt to then come up with a measure of the amount of operational flexibility. As you can see, because you have all these different devices, each device has its own characteristics. This problem becomes a multidimensional problem in terms of optimizing it and coming up with the right mix of what is providing flexibility. But this is one of the chapters in the book that I think if you're interested in the issue of flexibility from an operational perspective in terms of the calculation and the analysis, that's a chapter that I would definitely recommend And it's a chapter that goes into very deep assessment of the issue of flexibility. Now, besides being able to do a operational assessment of the flexibility needs and the actual flexibility that you have in your system, flexibility is also very much linked to the economics, because obviously moving these devices up and down to generate flexibility involves some costs, but then there's also the cost of even procuring these devices. So the next slide looks at kind of a straw man view of what one could call a flexibility supply curve. This curve was shared with me courtesy of Charles Smith. Charles Smith, he wrote the epilogue of the book. And what this curve shows you is that on a cost basis, you can see that perhaps one of the easiest ways to achieve flexibility in the grid is by looking at how you design your electricity markets. So in terms of low cost, currently you see that low cost as a source of flexibility, clearly looking at the issue of electricity markets becomes one that really helps very, very easily. The next one, which is perhaps one that we've dealt with before, is the issue of flexible generation. So both simple cycle gas turbines as well as combined cycle, but also there are some coal-fired plants that can also provide some level of flexibility. And then you have the traditional storage, hydro dam and pump hydro, that also provides some level of flexibility to the grid. Wind, both the wind and the PV systems, depending on how you operate them, can also provide flexibility to the grid. And then lastly, storage. And so the reason why I put this chart there, this curve there, because I think it's important as we analyze flexibility from the operational standpoint, one has to also look at the overall supply curve and the costs related to different types of flexibility resources. The other interesting thing to point out here is that even the wind and solar farms themselves can provide certain level of flexibility to the grid, and this is an area we expect to see a lot more research on in terms of the economics, as you may call it, the economics of flexibility on the grid. In the past, it used to be merely looking at your hydro systems and your combined cycles or your gas turbines. Going forward, we're looking at electricity markets, we're looking at other types of mechanisms to provide flexibility to be able to integrate higher penetrations of renewables on the grid. Now, let me just walk you through a few examples in the book that address the issue of flexibility. First of all, electricity markets. Electricity markets is being shown by various studies and is highlighted throughout the book that by designing markets, both real-time market, but also other forms of markets, the intraday market, the day-ahead market, how you go about committing units to the market, your capacity market, all of these different market mechanisms have the potential of providing flexibility to the system. Obviously, closer to real time, you have bigger impact immediately, but as you spread out, you can imagine flexibility being important, not just in terms of the real time, but also over the long-term operation of the grid. So that's where even capacity markets, financial transmission rights, all of these things that allow you to put other infrastructure in place to deal with this issue of flexibility can help, and this is why the markets provide a lot of mechanisms for increasing flexibility onto the grid. The next mechanism for flexibility, which is getting a lot of attention these days, is the issue of demand response. This chart graph is from the case study that was provided by Diane Broad and Ken Dragone, looking at the Pacific Northwest of the United States and looking at just how you can use, in this case, flexible demand to be able to smooth out the wind power production. And so you can see that by basically using flexible demand, you've been able to come in and smooth out the potential implications of variable generation and the impact it could have onto the grid. Now, besides looking at it at a macro level, the next slide gives you an idea of what are some of the other types of distributed energy resources that can actually help to provide levels of flexibility to the grid. So everything from cold storage refrigeration, residential water heaters, commercial HVAC controls, thermal brick furnaces, all of these devices that can, to some extent, allow you to increase or decrease the megawatts injection or extraction from the grid can provide some higher level of flexibility. And this is an area where we're going to see more attention, especially now as you're beginning to see new types of devices at this level of the grid that can provide greater controllability and therefore better flexibility. Now, that's in the Pacific Northwest. If you move to the eastern coast of the United States, where you have PJM, which is the largest electricity market in the world, the case study provided here is written by Andrew Ott from PJM, and this example here clearly demonstrates to you that demand response is becoming clearly a reality. You can see here from this chart the increase in demand response in the PJM market that we've seen over the past 6-7 years. And in essence, this trend is continuing not only in PJM, but we're seeing this trend in other markets around the world where demand response is being seen as a very easy mechanism for integrating higher penetrations of renewables. As the previous slide showed you, the previous two slides showed you, if you can get a better understanding of your load and how these loads perform, you can correlate the load and combine that with demand response, whether in a market mechanism, as in the case of PJM, or in other types of mechanisms as you may have in the Pacific Northwest in the U.S., basically to enhance overall integration of higher penetration of renewables. So you look at the chart from PJM, you can see that significant growth in demand response, and it's a growth that we see in an electricity market, not necessarily in a market or in a situation where you don't have a market. This is basically a market-based mechanism where you have demand response resources helping you to grow, to increase your penetration of renewables onto the grid. Now, I will just talk briefly about two other interesting aspects of flexibility that we see and that is worth noting, and that is the role of electric vehicle for the transportation sector. That, again, is helping to provide some level of flexibility as well as energy storage. Now, I say here, I call it the disruptors or game changers because the chapter in the book, there's a chapter in the book that focuses on distributed energy resources and the impact that these resources may or may not have on the overall operation of the grid and the potential it could have on the grid from a flexibility standpoint. There are challenges that will arise with regards to the penetration, higher penetration of electric transportation or even energy storage, but I think based on the studies we've seen, and there is a chapter in the book written by Duke Energy that looks at energy storage at the distribution level, and it shows how energy storage, in this case, was able to help minimize the impact of PV on the Duke Energy system. So again, interspersed throughout the book, you will see case studies that look at some of these technologies and then explore how they may impact and improve flexibility onto the system. Here's one example that basically not necessarily just focus on the book. This is an example that brings more of a real life experimentation, if you may, of a deployment of a mixture of these resources. This is a project from France in Nice, where you have, as you can see, an integration of multiple distributed energy resources that are providing flexibility service to help the grid. This system has photovoltaic connected to the system. They have energy storage. They have battery storage. What is important here is that this is being done both to benefit the distribution level as well as the transmission level of the grid. And this is a project that is ongoing. There are a lot of results there that you can actually see, an actual case study of where distributed energy resources done properly, controlled properly, optimized properly, can actually allow you to have greater flexibility on the grid and thereby have greater flexibility for integrating renewables onto the grid. Now, let me just briefly bring up two other topics that I think are relevant here. One is the issue of big data. I think in the book there's a chapter on big data, because as we're seeing more and more, the information that a wind farm generates, every turbine producing several megabytes of information every day, or every solar farm, all of this information is relevant to how you actually operate your renewable resources. One of the things that is driving the use of this type of technology, big data technology, and the importance for renewable is the penetration of so-called synchrophasers. Synchrophasers are basically measuring or sensor devices that are deployed in the transmission system. Those devices can be used to generate additional information that can be used today. In fact, in the book, there are 2 chapters dedicated to synchrophaser. There's one chapter that looks at the case of a synchrophaser units being deployed at a wind farm in Oklahoma. The chapter was written by Professor Luigi Vanfretti and Maxime Baudet from the Royal Institute of Technology, and Mr. Austin White at Oklahoma Gas and Electric Company in the United States. And again, there is another example of how you can use synchrophaser technology to deal with some of the operational issues with integrating renewables, and that is what the case study talks about. There is then also another chapter that looks at the use of PMU at the distribution level. That chapter is written by Alejandro Monmayer and Rezar Agadad in California at the California Berkeley University. That chapter again explores how you can use these technologies even more to increase penetration of renewables even at a distribution level. Now, let me just end with 2 slides, or looking at the future outlook here. First of all, what's next for renewable energy integration? So the book looks at a whole range of technology, looks at a whole range of policy issues, market design issues. Looking into the future, there are a couple of things that we want to bring up. The first thing that's very, very important is the evolution of electricity markets. We expect markets to continue to evolve, and we believe that evolution of electricity markets will definitely have a significant impact. The other dimension that I think is very important is the fact that as we bring higher levels of renewable energy onto the grid, we're expecting to move from a deterministic operational paradigm to a more probabilistic operational paradigm. And in that context, there's a chapter in the book dedicated to this, looking at how the advanced analytics on the grid will change as a result of this higher penetration of renewables using more probabilistic paradigms. And then I just want to, before I end here, I think there was one. Okay, yes. So the final slide here is basically one that looks at this issue of the improvement you will have in grid operation as you, again, do this transition from deterministic to probabilistic. And in that context, we expect to see even more advances in the overall integration of renewables. So in essence, what the book has shown us here, before I take the questions, is that at this point, renewable energy around the world is being integrated at a much faster pace. The challenges, there are still a few challenges in terms of improvements on wind forecasting, solar forecasting, but the significant penetration levels we've seen, the experience of grid operators, which is what is reflected in this book, as well as the advances in new technologies for sensors, meters, as well as using things like HVDC and others. All of these different technologies will only increase the flexibility of the grid by designing electricity markets, making them much more efficient. We will also see increased penetration of renewables enabled by the flexibility that markets will provide. So Hans, with this, I will stop here and go into the Q&A.